So welcome everybody to the second week of the 32nd International Conference of FPSAC. My name is Laura Colmenarejo and I will be the moderator today. As we have been doing for the previous sessions, there will be 3 speakers. Each talk will be 25 minutes long with 5 minutes in between for questions and a short break. The chat moderator for today is Bruno Benedetti.
Hello, buenos días. Hi from Miami. I have a technical communication for the chair of this organization, Alejandro Morales. Happy birthday to you. Happy birthday to you. Happy birthday, Alejandro. Happy birthday to you.
So yeah, happy birthday to Alejandro. I hope you're enjoying your day. And if you want, Joshua, you can share your screen.
Okay.
So let me introduce you to Joshua Swanson from the University of California, San Diego. And he will be talking today about on the distribution of the major index on the standard Young tableaus.
Okay, thank you very much for the introduction. And thank you to the program committee and all the organizers and everybody for the opportunity to talk. So I wanted to talk today about some joint work with Sarah Billy and Maciej Konwalinka. Basically, I'm going to try to summarize the results of 2 papers that are listed there. And there's archive links, and they've also both been published now. So a quick outline of today's talk. I'm going to talk about background and motivation for studying the major index statistic on standard tableau. Then I'll talk about a certain existence classification for which major indexes are realizable. We'll also talk about the distribution of this statistic on Tableau, and then we'll list a number of conjectures concerning unimodality, and maybe if there's time, we'll talk about further directions. So first off, just some background to motivate this whole thing. So I'm going to assume that you're familiar with descents and major index of words, very old notion, but for Tableau, it's a very similar notion. So here we have a Tableau, and we imagine going from 1 to 2, we didn't descend, so 1 is not a descent, but 2 to 3, we do descend, so 2 is a descent. 3 to 4, we go up, that's not a descent, etc. So in this way, we can construct a descent set of the Tableau. In this case, there are 5 descents, and the major index, as always, is just the sum of the descents. In this case, there ends up being 32. And so this generalizes the corresponding notion on permutations and words, and actually it's a strict generalization if you allow certain skew shapes. And all of this stuff was introduced 120 years ago or so by MacMahon. So just some additional notation for my talk. So I want to write the generating function for these major indices on fixed skew shaped tableau as SYT lambda over mu maj. And so the coefficients of this generating function, that is to say the number of standard tableau of a fixed skew shape with a fixed major index, I'm going to call these B, lambda over mu k's. And so why should you be interested in this statistic? Anytime anybody introduces maj, it's a little bit funny. But I claim that there's a whole bunch of great reasons. So first, it just naturally generalizes a bunch of really well-known and well-studied statistics. So the Q multinomials, the Q binomials, even in the straight shape case there, and the Q Catalan numbers are all embedded in these major index generating functions. Another, in my opinion, almost more important, but anyway, reason to study the major index on these standard tableaux is that there's just tons of connections to other areas. So I picked sort of my favorite connection here, the Lustig-Stanley theorem. So it says that the multiplicity of the symmetric group irreducible indexed by partition shape lambda in the degree k component of the type A co-invariant algebra, which has appeared in these talks already, is precisely this coefficient b lambda k. So counting tableau by shape and major index is the same as figuring out this, this irreducible decomposition of this very natural symmetric group module. So Lustig called these generating functions the fake degrees, basically because if we set q equals 1, we actually get just the degree of the corresponding symmetric group irreducible. And there's some more references that I won't go into. So some background for my work with Sarah and Maciej that will be the main focus of this talk is the following simpler version. So here I wanted to introduce these A lambda R's. So it's a less refined version of the maj statistic. namely the major index modulo n, where n is the number of cells of your partition shape. So we can think of this as the sum of some of these b lambdas, b lambda k, where k has a fixed residue class mod n. And so Sheila Sundaram asked in the r equals 0 case, when is a lambda 0? She had a specific conjecture. And then Kliachko actually implicitly, but anyway, he essentially asked the same question for r equals 1. I asked it for general S. And to spoil the surprise, here's the classification. So there's almost always a major tableau with major index r, given straight shape lambda mod n. There's just a few sort of degenerate families. So there's these 4, and then a few special cases, and you can read the paper for the precise statement. But the overall argument also uses a sort of probabilistic thought almost. So this quotient a lambda r over f lambda, this is the probability that a given randomly selected tableau of straight shape lambda has major index congruent to r mod n. And the point is that this differs from the uniform distribution by a very well-controlled error term. So that sort of gives most of the theorem. So then Sarah and I and Matej were motivated by the questions, sort of natural extensions of those questions. So when is the b lambda k 0? So drop the mod n thing. And then also, what does the distribution of the coefficients of these fake degrees look like? And then anytime you have sort of an enumerative sequence, you can ask a host of standard enumerative questions, for instance, unimodality. So first I'm going to go through existence. And we were able to completely classify when there exists a tableau, standard tableau of shape lambda with major index k. And the upshot is, so there's a minimum major index and a maximum major index, and everything in between is always realized outside of a few exceptions, the exceptions being rectangles with at least 2 rows or columns. And even then you only miss a little bit. You only miss the one above the minimum and one below the maximum. So this is sort of a very neat and complete answer to the existence question. But it also shows that it's at least somewhat subtle, because there are these infinite families of rectangular exceptions. So here's an example of this theorem. Here's the fake degree for shape 4,4. And you can see if I write out the coefficients, we skip the q to the 5th. So q to the 4th, q to the 6th. And similarly, we also have a gap right before the final coefficient. So those are what we call internal zeros. And so this theorem classifies the internal zeros completely.
Josh, there's a question from Maria Gillespie. Where do the a lambda r numbers come up, and why do we care about the major index mod r?
Sure. So those guys come up from induced representations of a Coxeter element up to the full symmetric group. So those guys actually track the irreducible decomposition of that. Some results of Kreskevich and Wayman. Yeah, good question. Thank you. So our overall approach to this internal zeros argument is to construct a map that sort of combinatorially increases Madge by 1. We can't literally always do that. If we started with, for instance, a tableau with maximal Madge, then we couldn't bump it up, but usually we can. And so our approach uses 2 operations, sort of rotation rules and block rules. And so I'm going to very briefly describe each of them. So the rotation rule to bump up Madge by 1, I think the example is the important bit. So we apply a cyclic rotation to some elements of the tableau. So here, 5 goes to 4, 4 goes to 3, 3 goes to 5. And if you track what that does to the descent set, it bumps the 2 up to a 3. And so that will increase the major index by precisely 1. And so we gave a certain combinatorial characterization of rules of this sort, which will always bump up one of the descents by exactly 1. Okay. And so these rules actually, they exist in quite a lot of generality. For instance, if you have 1 as a descent, then we showed that you actually can find a rotation rule to bump up Madge by 1. However, once in a while there aren't. So like 24 out of the 81,000-ish in this particular shape simply do not have a rotation rule. And really I think conceptual reason for that is that the rotation rules, they fix the number of descents. And that can't possibly be right in general, because different standard tableaux of a fixed skew shape, will have differing numbers of descents in general. So we had to introduce the second sort of family of rules, which we called the block rules. And I'm not going to try to describe them at all. They're a little bit ad hoc, especially compared to the rotation rules. But the upshot is they add one more descent, and they bump up Madge by 1 as well. So if you actually think in terms of this sort of bi-statistic, Madge minus des, the rotation rules bump that up by 1, 0, because they fix des and increase Madge by 1, whereas the block rules bump it up by 0, 1. And we actually go through a bunch of cases and construct the phi map that I said sort of very explicitly, but it's pretty technical. Though it's important that the argument is sort of much more powerful, in my opinion, than just positivity. It really puts a poset structure on the set of standard tableaux of a given fixed shape. So we constructed this poset P of lambda, which is on all the tableau if there are no internal zeros, or if there are internal zeros, we just chop off the min and max. But anyway, the actual relation is just, we define our rules basically to be the covering relations. So the rotation and the block rules are covering relations. And then also there's this sort of duality that I'm going to sweep under the rug. So we throw in a little bit more for some duality reasons. But anyway, the upshot is that the P of lambdas are ranked by the major index, and then also this bi-statistic Madge minus des. And you can see some Hasse diagrams at Sarah's website here. And just a very brief note, so cyclage is another standard ranked poset structure on standard tableau. However, it doesn't at all restrict to fixed shape, and we were unable to make it sort of useful. So this seems sort of fundamentally more different and difficult somehow. So some consequences, as I said, the major index generating functions have almost no internal zeros. Also, the descent generating functions has literally no internal zeros. That's answering a problem of Adin, Elizalde, and Reichman. And actually, on Friday, Vasu Tiwari gave a talk and got me to talking with his co-author, Philip Nadeau, and they actually also have a simple argument proving this. Both of those are actually in the straight shape. It turns out that if you combine Vasu and Philippe's argument with Adin, Elizalde, Reichman's, you can actually get the skew version as well. But it's also an immediate consequence with basically no extra work of our work. This funny Madge minus des statistic also has no internal zeros. And moreover, we were able to amplify this up to essentially all complex reflection groups outside of the exceptional ones. So the details are there. This includes the type B and D cases specifically. And then also as a corollary, you get a new proof of my original A lambda R classification. Okay, first part done. Second part is to talk about the distribution of the major index statistic on these standard tableaux. So the idea is we kind of want to plot the list of coefficients of these generating functions. So you do that and you get something like this. So in this shape, in this case, we have this kind of triangle. Over here, we have a very sort of nice normal looking curve. And in all three of these cases, I've overlaid a normal curve with the same variance and standard variance and mean over the original data. So you can see there's kind of something happening in between. So this is not normal. This is mostly normal, but a little weird. And this is basically normal. So heuristically, at least, there's just a central limit theorem, but there's some sort of degeneracy going on. So our first sort of order of business was to figure this out. What is going on? When is it asymptotically normal? So first off, we actually defined this notion sort of measuring the degeneracy in some sense. We call it aft. So the aft of a partition is the number of cells minus the larger of the number of cells in the first row or first column. And so I think the picture makes it much clearer. All of the cells not in the first row or first column contribute to aft. And then also the cells that are in the first row or first column, but not in the other one of those two, contribute to aft in such a way that the result is sort of smaller. So here the first column cells that weren't in the first row also contributed. And so you get this, I said it was kind of measuring degeneracy. Well, it's easy to notice that aft is precisely 1 if and only if you're of this n-1, 1, or 2, 1 to the n-2 form. And those are 2 of the degenerate families for the A lambda Rs that I had mentioned before. So this sort of, I think, indicates that this is probably along the right direction. So this statistics is on FineStat. I will say the words representation stability and leave that there. Okay, so I wanted to give a precise sense in which these statistics are becoming closer to the normal distribution. So here's the standard way to do that. So first, the x star for a random variable x is the standardization, where you just shift it and scale it so that it has mean 0 and variance 1. All of the random variables that I'm talking about are very well behaved, moments of all orders, you know, tightness is no issue, it's all very fine, so I'll ignore anything like that. So a sequence of random variables is called asymptotically normal if the cumulative distribution functions converge pointwise to the cumulative distribution function of the standard normal. So that's the standard machinery involved in the central limit theorem. So we introduce the random variables x lambda madge for the major index statistic on standard tableau of a fixed shape, just uniformly sampled. And now you might think, well, madge is a sum of descents. You know, there's a ton of central limit theorems that say you add a bunch of random variables and you get normality. Unfortunately here, the random variables involved are neither identically distributed nor independent. And also, as you saw in the earlier picture, like, it's not always going to be normal. So there's definitely some sort of subtlety in here, even if sort of the generic thrust of things is towards normality. So we actually were able to completely classify when a central limit theorem for the sequences of these major index statistics on straight shape partitions is asymptotically normal. So the result is that you get asymptotic normality if and only if aft goes to infinity. Which of course begs the question, well, what happens if aft doesn't go to infinity? Do you have interesting non-normal limits? And so we also have a more general theorem there. So here we're looking at the normalized statistics, and they converge in distribution. So if and only if these 3 cases occur. So the real new one is this 2. So that if the aft converges to some finite fixed value, then you get what's called an Irwin-Hall or uniform sum distribution. And the details perhaps don't matter super much. So I kind of conceptualize, we didn't say this at all in the paper, but I kind of conceptualized this particular result as classifying a compactification of the moduli space of these normalized distributions. So, and you can technically make it precise. So we have these Irwin-Hall distributions that are sort of tending towards a normal distribution. Then we have this kind of cloud of individual madge distributions surrounding them. And you can say that this does give a compactification of that space. So how do we prove it? We use the method of moments. So the method of moments says that if the dth moments converge, then you get convergence distribution. So moments are frequently very unwieldy to work with in practice. We actually used cumulants instead. They're like moments, but better. I strongly refer you to section 2.2 of our paper because we wrote it for combinatorialists to just kind of get you up to speed quickly on the lovely properties of cumulants. For this talk, just the first cumulant is the mean, the second is the variance. So those are some nice properties. But anyway, you can replace moments with cumulants in the method of moments. So the key, this formula right here is actually one of the highlights of the talk, I think. So it gives an exact formula for the cumulants of the major index statistic in terms of the hook lengths of the shape lambda. And why I say it was key is because whenever I was talking with Percy Diaconis about this, he gravitated towards this formula as the key. So how this formula works is it actually follows from Stanley's Q hook length formula, very lovely formula. And then there's actually a general formula for the cumulants of quotients of Q integers. I'll let the slides speak for the history of that formula. So some consequences of this asymptotic normality classification. We get a new proof of asymptotic normality in a whole bunch of cases that were already known. So for the Q factorials, the Q binomials, the Q Catalan numbers, the Q multinomial coefficients. And so we've given now a common framework for all of these, all simultaneously, which I find to be just very beautiful. So the last thing that I wanted to talk about was unimodality conjectures. So some initial observations about unimodality of these major index sequences. Well, first off, for the Q binomial case, the unimodality goes all the way back to Sylvester 150 years ago. And if you read the paper, he was very, very excited. I encourage you to look at it. It's kind of cute, actually. But anyway, there's other unimodality connections. So like these Q multinomial coefficients are known to be unimodal by Hard-Lefschetz theorem applied to partial Flack manifolds. So there's sort of a lot of big tools available for some of these distributions. However, as we've already shown, there are internal zeros sometimes, namely for the rectangles. So unimodality must fail for general n. So we have some conjectured classification of which shapes lambda are unimodal in terms of the number of corners. So corners are cells with hook lengths 1. And so I refer to the paper for the explicit version, but if you have at least 4 corners, we claim that you're unimodal. In another direction, we have a conjecture concerning the actual approximation of these B lambdas. So our central limit theorem says that the cumulative distribution functions converge pointwise to the cumulative distribution function of the normal. But what about the density and mass functions? And so this is what's called a local limit theorem. And this is what I got for the A lambda R's. The Maj mod n, but it seems to be much more delicate for the B lambda R's. And these local limit theorems are well known to be very notoriously technical. I have a good number of ideas, but I've kind of hit some snags. So in any case, this result at least sort of mostly and heuristically implies unimodality. But the most important conjecture I wanted to get to actually is this last one. So we call a sequence parity unimodal. So we kind of weaken the literal unimodality by saying, okay, let's just make sure that every other entry is unimodal in the 2 sequences. So the sequences of evens and the sequences of odds, we require each of them to be unimodal. And Eric Stuckey showed that the Q Catalan numbers, Q Catalan coefficients, that is to say the coefficients in the NN case, are parity unimodal. So that's some evidence. And actually, we conjecture that it's true for all lambda, full stop, no exceptions. And the evidence for this is that it's true for all n less than or equal to 50. It's pretty decent. It's consistent with and would imply the internal zeros classification. So Stuckey's argument actually constructed an SL2 action on rational Cherednik algebras, which in some philosophical sense was a very similar approach that Sylvester took. He also constructed an SL2 action. Of course, Stuckey's argument is much more complex. And actually Mark Heyman included a parity unimodality sort of prototype in the context of some diagonal coinvariants. We've been unable to prove this, but I feel like this conjecture is sort of ripe for somebody to have the right idea. So I hope after this somebody will tell me how to do it. Okay, that is it. Thank you very much. My references are here. A lot of references.
So let's thank Joshua again. If you can stop your sharing and see everyone's saying that you did a really good job.
Okay, thank you. I'll have to get the chat up. There we go.
So we have 4 minutes for questions. Bruno, you can go ahead.
Thank you very much. The first one by Bruce Westbury, which asks about connections to the representation theory of the zero-Ecke algebras. Bruce, you can unmute yourself if you need to add something.
Yeah, I'm sorry. I don't know very well. I would need more specific questions, I think, as well.
Okay, all right, thank you.
Hi, Bruce.
Hi. Hi.
Next question, Jake Andrew Levinson. What about modular unimodality, mod R for other R?
Yeah, so I've thought about that a little bit. I haven't really checked it. So I feel like there's not much motivation at the present. So like, for instance, if you go back to Heyman's argument that I referenced, this parity unimodality kind of comes across very naturally from the SL2 actions and just how the degrees work out. Whereas I just haven't seen it appear anywhere else. I certainly would be very interested if you had like an R-arity unimodality. That would be cool. I'm not aware of anything like that though.
Chaim Eben Zohar asks, in the central limit theorem, what is the asymptotics of the variance in terms of n?
Let's see, so the asymptotics of the variance is theta of aft times lambda, theta of aft times n squared. And in fact, the asymptotics of kappa d is aft times n to the d, and that's how we prove it.
There's a question by Ben Young, on which Sam Hopkins commented already something, but maybe from you, what do we know about the distribution of the descent set itself, say for large square standard Young tableau?
Yeah, so I don't actually know that much about the distribution. So I mean, like Adina Elizalde-Roykman, like even the support of it was an open question in their paper from 2 years ago. And it turns out that it's not that difficult to actually construct these guys and classify the support. But yeah, like I think it would actually be potentially quite interesting to know what, like the analogous question for the distribution of des. But yeah, I don't actually know the answer.
More questions? If not, I'm giving back the line to Laura.
Thank you.
Thank you so much.
Just a reminder, I will still copy all the questions to the Slack chat, and if anyone has any other comment, just please go there and continue discussing.